For several years now, scientists and manufacturers have become increasingly interested in microalgae and their wide-ranging potential for application. Microalgae are already present in our daily lives in some cosmetic, pharmaceutical, and food supplement products. In the long term, and on a much larger scale, they could even represent an alternative to certain food ingredients, which would of course involve mass production. As microalgae cultivation technologies emerge, it is therefore essential to find ways of mastering the techniques on an industrial scale. This is one of the aims of the ALG-AD project. Cultivating microalgae is a delicate matter because not all species of microalgae have the same physico-chemical requirements for development. Microalgae can call on different types of metabolisms to create the organic matter they need to grow and multiply. Autotrophy is the most common type of metabolism, where microalgae can use inorganic carbon in the form of carbon dioxide and light as a source of energy. Heterotrophy is where they assimilate organic carbon such as glucose in the absence of light. And finally, mixotrophy, where they are metabolized both autotrophically and heterotrophically. Therefore, to cultivate a particular species of microalgae, it must be provided with the correct amount of light, nutrients, carbon dioxide and minerals. In seawater, freshwater or brackish water at a controlled pH and temperature. There are currently 2 cultivation methods which are selected according to the type of production required. In open cultivation, the microalgae are placed in raceways or open ponds, where paddle wheels are used to mix the microalgae. Although this is an inexpensive system, productivity is impacted by the risk of microbial contamination, loss of water through evaporation, and seasonality. It is not easy to grow algae during a European winter, and the pond may have to be placed inside a greenhouse for protection. In addition, the cultivation parameters are difficult to control. In bioreactors, microalgae are placed in transparent, flat, cylindrical or tubular containers and are exposed to either sunlight or artificial light. This closed system, which is relatively expensive, makes it easier to control the cultivation parameters, and productivity is barely affected by external hazards. Each of the 3 ALG-AD pilot sites is focusing on a particular cultivation model with the aim of testing a maximum number of parameters under real conditions, including different types of digestate. At ALG-AD in the UK, Chlorella vulgaris and Desmos obliquus are grown autotrophically in a 5,000-litre tubular photobioreactor, and the biomass is harvested and concentrated for mixotrophic cultivation in a 350-litre reactor. At InnoLab in Belgium, a consortium of Desmos and Chlorella are grown autotrophically in a 3,200-litre tubular photobioreactor. On the Lombard pilot site in France, the heterotrophic microalgae, Aurantiochytrium mangrovii, is cultivated in a 1,500-litre cylindrical reactor. These are all avenues that could potentially lead to the implementation of manufacturing solutions.